Hello everyone, my name is Anthony Shivkumar, and in today's video we're going to try to download the ARM GNU compilers and try to use the Linux environment to compile embedded system codes and deploy it onto a microcontroller. And generally speaking, when you say buy a development board, whether it be from say Nordic Semi or from LPC or from NXP or from Texas Instruments or from Microchip, they try to force us to use their own IDE, which is generally Eclipse based or Visual Studio based, and there's nothing wrong with that. But say for example, your project comprises of different microcontrollers. One maybe from Texas Instrument, one maybe from NXP, one maybe from Microchip, and you're using a combination of all of this. Imagine you had to switch between every IDE just to compile code and run it onto that particular processor. Now, I generally don't think that's a great idea. It's not scalable. So one of my solutions is to, have one repository that will allow me to write just general code that's, maybe that might be ubiquitous or might be, common to different targets that I want to deploy on. And have a very specific folder that deploys to a specific, hardware-specific target. And I want one repository that, has all that rather than using different IDEs that is given by the manufacturer. And that's really what we're trying to accomplish today. So we're going to use the Linux system. That's generally my, my go-to operating system of choice when it comes to developing and writing software. I do have a Windows host machine, so we're going to use Windows to download some of their IDEs to make sense of what's happening under the hood. Take some of their makefiles and the code or the build part of what makes how they compile the code. Take some of the concepts or some of the syntax and then deploy it and create our own makefile so that we can run those code and generate say object files and eventually compile the software for that particular target. So let me show you what I'm trying to do to make sense of it. So what I have over here, I'm just going to open my Linux environment. So I have this repository called Anchi Robotics. And here I have say, two main folders. One is the source folder and one is the include folder. So let's go into the source folder just to give you a sense of, how I want to structure my code. It's not written in stone, probably going to change, but, I just want to, showcase as to how I'm planning to organize my code for this complex, autonomous drone system. And I want to use my Linux environment to do it. That's really the idea of why I'm doing this. And under my under my source directory, I want to have say different folders for different parts of the drone. And some of it might be flight control specific code. Some might be computer vision specific code. Some might be machine learning specific code. The real-time operating system, sensor fusion. Now, I might probably organize this code into something that's more usable. But my point is, I want to have my code separated this way. I don't want to have my code separated based on the target that I'm programming. I want the code to be common, my target to be very specific as a subdirectory. So I want all my target-specific folders to be under the target directory. And all the other parts that are important for making the drone fly should be, that should be part of my repository or my core library. All right. And if I want to download to a specific target, this is where I go to the target, and this is where I would have all my specific, hardware specific code. So if I'm using the Nordic Semi, I'll have a code for that particular manufacturer. I actually should have NXP over here. So what I'll do is, make directory. I should actually create an NXP directory, but these are all NXP processor. There's 32. So I'll actually do this. So make dir NXP, and then I'm just going to move my KV to NXP. I'm going to move my LPC to NXP, and I'm going to move my S32 to NXP. And I'll show you what I mean, why I'm doing this. So now when I look at my targets, I have, two manufacturers, Nordic Semi and NXP. Tomorrow, if I want to use, say, NVIDIA, or if I want to use Texas Instruments or Microchip for the Arduino, I would have all those targets in this particular directory. So my root directory would still be anti-robotics. The source would have, different types of algorithms, mathematics, the control systems, the machine learning and artificial intelligence. And one of those directories will also be target, and that will be very specific to the hardware. And then when I go to NXP, say for this particular example, I'm trying to compile for the LPC 1769. So I can go to the LPC 1769, and there I will have all the board support packages. Now I'll show you how I got this code, but that's how I want to organize my code, so that I am not relying on the IDE of the manufacturer. So that's in a nutshell what we're trying to do. So before we get started, how do I compile code right now? You might ask, okay, this is nice and fancy, I got everything the way you want, but how are you going to compile the code? The IDEs generally give you all the code to compile, so how are we going to do it? So we're going to break it down, all right? Because under the hood, it's doing something that's building code, right? So it's still compiling C code into a target. So let's figure out what it's doing. So in this particular case, if you just search for ARM GCC compiler, so if you just go on, any search engine and search for GCC compiler, you will come to this page called the GNU ARM Embedded Toolchain Downloads. All right, so click on this. It's free. It's open source suite. And in here, after you download this, after you come to this page, you need to download the GCC, the GCC ARM Linux Starball. And in my particular case, I basically installed the x86-64. So I went to my Linux machine. I go to my Linux machine, and then under here, I've downloaded everything. So I'm just going to go to my vertical. I download the file and I unarchive it. And I basically installed it under my programs directory. This is a private directory that I've created. Generally, this is how I organize my code. And what I have over here is an ARM folder over here. Okay, so generally on my I create a directory called programs, where one of the things that I do with my operating system, especially my Linux operating system, I rarely use sudo apt-get. I mean, it's very rarely that I try to avoid as much as I can. Like if I want to install PHP, I will actually download the source code and compile it. This is generally what I always do. So all my compiled directory code will always be in this particular directory, programs. This is just the way I like to work, so that I know and I have full control of what version I'm installing, what add-ons are installed in there, and where all my code is. So if I want to upgrade it to the newer version, I can just, git pull that repository, build it again, and it'll be installed exactly where I want. That's just the way I like to work. And that's the reason why my ARM is in this programs directory. So under the ARMS directory is when you download it, it'll give you the GCC ARM non-EABI thing. Let's go over here and let's see what is in this particular directory. So they have the bin, the lib, and the share. So if we go to cd bin, we can see that all the I did just a few weeks. If you look at my videos on what is GCC, what is GCOW, what is how does the compiler work. That's all relevant to what I explained in the previous videos, because ARM is just using the same GCC code. The only difference is compiling into the thumb instruction set so that it can be deployed onto a target. That's really the difference. So that's the reason why it's an ARM specific version of GCC, because it's compiling into the thumb instruction. That's really it. But it has the same thing. It has, the assembler. It's got the archive. It's got the CPP. What is CPP? It's not C++. This is the C preprocessor. And we had if you watch the video, it's on the top left, top right, how does GCC compile its code? I explained to you, what all of these binaries are, because when you use the GCC compiler, it is going to use these executables or these software to basically compile your code, and each one of them is making the processing your pre-processing parts of your code, converting your assembler, doing the linking, and then creating the executable, and it's all part of it. They give you the GCOW, they give you the GDB. It's giving you all the code of basically what GCC has. So now once you download it, now we need to figure out how to use this. So what I'm going to do over here is I'm going to use my LPC1769. The reason why I'm using the LPC1, you can use any target you want. The reason why I'm using it because I have a development board, and I created my own development board using this target. Is I'm going to go to the NXP website right now. So when I go to the NXP website, so make sure you unarchive all of this, and then you're just good to go. And then I'll show you how we're going to write a makefile to use the path from here. I don't recommend you use sudo apt-get, but it's up to you. It's a preference. I do have my reasons. I'm not going to explain it to you in this video. I do have my reasons as to why I always, try to download it and put in a folder that I know where it is. It's not in this user bin, root folder. It's in my home directory, or all the tools and all the binaries that I want, and I'm installing. I want to have full control where they are. It's just my way of working. Okay, that's you go to the NXP thing, and I'm looking for the LPC1769. 1769. That's the microcontroller I'm using. We could do this very well for the Nordic Semi, for their ARM processors. We could use this very well for the Texas Instruments. This could be very well for the ST32. It doesn't matter. And that's what I want. That's why I'm doing this, because I want to develop code that makes it agnostic across any target. So if there's a chip shortage on one processor, I can just switch and move it to the next target. That's really that's really what I'm trying to do, is have that a rapid way of prototyping and making my products and moving faster, rather than saying, oh, I don't have this target, or my code is dedicated only to this particular hardware. Now I gotta wait till this chip comes in stock, and and all that gibberish. We want to avoid that. So you go to Tools and Software. Each website would have their own version. In this particular case, again, I'm just giving an example of this particular processor, of this particular microcontroller. And then you go to the board support packages. And what this does is it gives you all the necessary libraries. Most manufacturers will do this for you. They'll give you all the libraries so that you can, start writing code for that particular target. It'll give you this high-level abstraction of mapping the address with the actual pin of that particular microcontroller. You don't really want to do this. This will be given to you by the manufacturer. It's all of these, the low level code, corresponding. If I put a pin out and say, I want to multiplex this particular pin to a GPIO or an I2C protocol, an SPI. It's got to target that specific pin on that particular microcontroller, and that pin will be under a particular port, and you want to access that. So the manufacturer gives you that code saying, okay, if you write the C code, it's going to go to that particular pin and activate it. And it's you really don't want to write that part of that piece of code. You want the manufacturer to give you, and that's exactly what I'm trying to download right now. So if I go to the BSP, which is both support packages, I am going to download the LPC software development platform. LPC Open is what it used to be called. It's a pretty old processor, microcontroller, and I'm using the LPC1769, the board that I already have, and I've already downloaded it. So this is a Windows system. So when I go to my Linux system, I will download it, and that's what I have in this particular folder. So when I go to my source, I go to my target, I go to NXP, I go to LPC1769. That's exactly what I've downloaded. So in here I have all the different. These are all examples of how to get started using the development board, such as how to get the blinky working, getting a particular LED going on and off, how to test your I2C protocol, how to test your SSP protocol or SPI protocol, how to use a different real-time operating system called UCOS, or the free RTO system to blink. So it gives you examples. But there's one thing that it also gives you are these two folders. One is the board package and one is the LPC chip 17566. So let's go into here, because this will be relevant to any microcontroller you use. Actually, we should go to source this and let's open up this guy, LPC chip. All right. Now in this chip directory, what does this have? So this has all the, as I mentioned, this does all the multiplexing, or converts the, let's go to say a particular type of particular code, what do you say, particular GPIO. So this will map all the, this will include chip. Let's go to where's the, is it in the libs? No, it's under include. Yeah. Okay, so here we'll go to the chip. It'll, it has all the header definitions and the pin mapping, and here we can go to chips, where we can go to GPIO, and here's where all the pin mapping with the exact offset and the address offset. It's given by the manufacturer. So you don't really want to touch this code. You want to basically use this code. So it basically gives you an abstraction from writing high level code, so that you can access the pin and do all the multiplexing. So what you want to do when it comes to this is you want to create the library. So when you download, say, the McuXpresso or the manufacturer IDE, it'll give you a bunch of code over here. And in this particular case, I'm going to take this particular makefile that they have over here, and I'm going to invoke what we downloaded. We downloaded the ARM none EABI, and it's using that to compile this code. So what we'll be doing is, taking examples of how this makefile is written, put it into our folder, into our directory, create our own makefile, try to use the ARM GCC that we just installed, and from there we'll try to compile and see how that works. All right. So what I've done is I'm going to open my makefile, which I've already written. So I'll go to the cd/lpc underscore chip vi, and then let's go to the makefile. And this is what I've written. So this is not, and how I've written it is basically I have copied the makefile that is generated by this IDE, which is the McuXpresso, which the manufacturer gives you. I basically just copied this whole part from this part. And wherever the path is, in this particular case, the path that they have over here is, let's use the ARM none EABI GCC. So ARM none. All I got to do is find the path where this is, where my GCC is installed in my Linux system. Similarly, the size operator, where is it installed in my Linux system? That's really what I'm trying to do over here. And that's what I basically have in this part of the code. So I've basically got the ARM path, which is where my ARM code is basically, where I've installed all the GCC, which is over here, is in this particular directory. And then I've got my C compilers GCC. My AR is the archive contract. Archive is basically generating shared objects shared objects or static object files. That's why you use the AR. Then you have the size, then you have the clib, and then you have all. So that's really what I've done over here. I've already compiled it. So what I'm going to do is I'm just going to do a make clean. And what this does is I have the include lib makefile source. And if I just do a make, it compiles. So now I've basically taken what the manufacturer has given us through the IDE, and now I'm able to do this on my Linux system. It's pretty cool. This allows me to now work in my environment using the setup that I want, using the folder structures that I want, because now I understand how to make this work. As in that, I generally feel, you just have power over all of this. Now, when it comes to debugging, and the IDE does offer a lot of other visual ways of debugging, especially when you're downloading code to the microprocessor and seeing how things work. We'll get to that later on. But my goal over here right now is to just form a repository, form the folder structure, see if everything is working, get all the gears working, and then step by step start to include all the the debugging, the testing, and make it more for production ready or a more deployment ready, so that you can rapidly prototype. So let's do the other part, and then we have another folder over here which is very specific to the board. So if you buy the LPC 1769 Expresso board, this is what it basically they give you another. I'm just going to do a make clean again. They give you let's look at what it is, and generally a lot of a lot of manufacturers will make these development boards for you, and the development boards will basically say, okay, this pin is connected to say an EEPROM, this pin is connected to a motor driver, this pin is connected, and that's what this particular folder is doing, is basically having an abstraction over the one that we just compiled, which is very specific to the board based on how the PCB is designed basically. So the first one that we compile for it is literally doing all the mapping of the GPIO pins and the I2C and all the actual pins, and the port is all come with that particular address in terms of the address mapping. Whereas you're just creating an abstraction of saying, okay, now this particular board has certain pins connected to certain parts and certain peripheries. Let's get those activated. That's really what it's doing. Like if you have an LED, which part of which blinky is going to work? You want that blinky and port C, pin number 3, those are the kind of things that this particular folder has. So let's compile this. I'm just going to go and do make. And once again, it's compiled. So when we click in ls, it's basically generated the A file. The .a is basically a static library. And that's pretty much what this video is all about. So what we have done this in this particular video is we have created our own folder structure, as we have over here. We have downloaded our ARM, all the ARM library, ARM binaries. And once we've downloaded all the ARM binaries, we have basically then downloaded a microcontroller of choice, in this particular case LPC. I will probably do a video for the Nordic Semi, and if you have a microcontroller of your choice that you want me to do, show you how you can deploy this on your Linux system, let me know, and I can get that working too. The principles will be the same. It's just a matter of fact of the code and the actual target code will actually just be different, but the principles of how to do this will be exactly the same, as long as it's an ARM, as long as it's using the ARM compiler. And then from here, once we created our own directory structure, which we feel might be something that we can work with. We have a target folder, and then from our target, we downloaded the one that makes sense to us, which is the board that I have. And then from here, we basically installed the core library, the one that is we created a shared object. We created a static object file from which now all these projects will now be linked to this particular core object. So we created the static object file, and now when I compile for the periphery blinky and download it into the board, which I'll do in the next video, that will now link to this object file that we compiled over here. So if I go to cd.this, this is a particular object, cd.6x. This object file will now be linked to all the other projects in this directory, which can be downloaded into the target hardware, will be linked to this object file. And if it's very similar to the board, I can even link it to this the object file that we created even over here. So if I do a cd, or I do an ls /, even this object file .a will be linked to all the other projects that we have over here. And this is just a way to get everything working. And over time, you wouldn't want to use what they've given you. You might want to write your own projects. You're not going to do a blinky. You're probably going to have, say, how to control a drone. You're going to have motor controller. You're going to have connecting to your IMU sensors and all the cool stuff. So this just gives you an idea of how to write the code when you're using a specific protocol and how it works. But from after that, it's a matter of customizing it for your own project. That's really it. So I hope you like this video. If you'll subscribe to this, because a lot of what I'm trying to do is build everything from the grounds up. This is robotics. There are a lot of things that it's very easy to download things that's out there and get something started quickly, and nothing wrong with that. But if you want to be nimble, you want to have the ability to choose your own microcontroller and get started, right from, it doesn't matter. I don't want to be reliant on a particular hardware or manufacturer and have my own repository and go from there. That's really, the kind of thinking and process that we're going to, that'll be pretty much the aim of this particular video series. And that's the reason why I made a list of, all this. I made a video on, what GCC is and what is AR, what GCOV is, how does the compiler work, just to get familiar with, all these tools, because once you start to develop for embedded systems and do much more sophisticated stuff, this basic knowledge is very important. All right. So please subscribe, like the video, comment below if you have any questions. If you want a different microcontroller we want to do this for, let me know. And until next time, take care.